Hello everyone, next I will introduce you to the topic of engineering design and 3D modeling. Once our design concept is drafted, we will deepen our study. In terms of design performance and design implementation, we hope that students can make good use of digital design tools to deepen and broaden their extended studies, such as the design sketch completed by students regarding its design modification, detailed structures, spatial organization. If digital tools can be used, whether it is for the photorealistic rendering for 3D models or the modification of structural details, it will be more convenient than hand-drawn sketching. At the same time, if 3D drawing tools are used for design modeling, it can also be used as an objective data analysis for engineering design. Predictive analysis is an important learning ability in our in-depth learning, which will further serve as a problem-solving and design thinking method. Also, for its design implementation, especially regarding prototype manufacturing, modern 3D tools combined with digital output equipment such as laser cutting machine, 3D printer, CNC engraving machine can make students' ideas come true more quickly, while also improving the quality of design and manufacturing. Therefore, for the design implementation part in the in-depth learning course, students should use the digital output equipment as much as possible so that through the process of concept development, 3D modeling, and predictive analysis, the model can be further outputted and go into testing assessment after engineering design prototype manufacturing so as to make the test and evaluation more objectively accurate. This is also an important reason for learning how to make good use of digital tools as output equipment. For the learning of 3D modeling methods, here are 3 main learning tips. The first one is spatial thinking. You need to learn to dissect the problem and disassemble the overall shape or structure into smaller parts that can be handled. For example, this Le Mans racing car at the lower right corner, we can disassemble its tires, wheel hubs, cockpit, rear wheel arch, spoiler, and chassis, part by part, and then combine them together to complete this Le Mans racing car. The second tip for learning 3D modeling is to familiarize yourself with the commands through modeling exercises. These commands are all assembling methods for 3D elements. Through this practice of disassembling, assembling, and shaping, students can effectively create the 3D models needed. Therefore, familiarizing with the commands is also an important learning process for learning 3D modeling. The next step is a comprehensive modeling thinking, which is mainly to simplify what is complex. You can first observe whether there is a clear contour or boundary in your design model. For certain modeling, we use additive construction. For some others, we do the opposite and use a subtractive method to complete the final shape we want. These are modeling design thinking, flexibly applied onto 3D modeling tips. Therefore, mastering the modeling rules is helpful for learning 3D modeling, especially for later on when students want to create their own 3D models. Mastering these rules is very important for future design modeling. Here we will briefly introduce some commonly used 3D modeling commands. The first command introduced is extrude. For extrude, we create a contour line, such as a square, and we turn it 3-dimensional. This 3-dimensional process of extruding the square into a cube is called extrusion molding. As seen at the right, there is a concave-shaped contour. We extrude it to make a 3-dimensional concave-shaped square, which is a modeling concept for extrusion molding. The second commonly used 3D modeling command introduced is revolve. For revolve, we create a contour line from its side, such as an arc with a waistline, and after rotating it around the central axis, it will become like a vase with a waistline. This concept is called rotation molding. On the right, we also use a concave contour line. We do a full circular rotation around the central axis that is outside this contour line, and we get a hollow 3-dimensional shape similar to the tire structure, which is also an application for rotation molding. The third commonly used 3D modeling command Introduced is loft. Lofting can use different cross-sectional contour lines. For example, we use a large-sized ring and a medium-sized ring followed by another large-sized ring. Each ring is a bit like the concept of making a lantern. We use cloth to stretch it up and wrap it around 3 or 4 different rings. The shape formed in this way is called lofting. Therefore, we can use the same contour line or completely different contour lines as long as it is either a closed loop contour line. Matching another closed loop contour line or an open loop contour line to another open loop contour line can be used in loft command for shape forming. Finally, we will introduce a very commonly used 3D modeling command, sweep. For sweep, after a contour line is created, we set out a path. On the screen, we use a circular cross-section as the cross-sectional contour line and an S-shaped wavy line as the path. After sweeping, it will become a curved shape, similar to a water pipe. On the right, concave outline is also used, and also a wavy path is used. Such cross-sectional outline following this path, the shape we get is a curved 3-dimensional shape that you can see here. From the 3D modeling commands introduced earlier, let's think about how this water canteen is drawn. From the disassembly of the space problem, we can divide the kettle in the lower left corner into 3 parts: the spout, the body, and the handle. On the right is a breakdown explanation of these 3 parts. For the canteen's spout, we completed a small oval cross-section and a large oval cross-section, swept along this path to make the shape of the spout. For the canteen's body, the top is a small circle, and the bottom is a large circle cross-section. We make the shape of the body through lofting. For the canteen's handle, we draw an up-laid circle, swept it along the hook-shaped contour line to complete the handle. Therefore, this canteen can be completed using these 3 3D modeling commands. We have introduced some basic concepts of 3D modeling and some tips for modeling. Next, we will go through actual operation of 3D modeling. The software used for demonstration is Rhino, which means rhinoceros in Chinese. The 3D modeling software is used in engineering, which is generally used in industrial product design. Generally speaking, it has the following 5 main features, which is why we choose to use it. First, it can create a variety of 3D shapes free of any constraints. Second, it is a software that is easy to learn and users can concentrate on the design of the concept idea, without spending too much time learning about the commands and parameter settings. Third, its precision. It is accurate enough to meet the needs of the various stages of design, digital manufacturing, and engineering analysis. Fourth, its software compatibility is very good. It can combine with other designs, drawings, digital manufacturing, engineering analysis, and other drawing software which can be used together. Fifth, its hardware requirements are very low. It can perform very well in ordinary laptops. On the right is shown survey on software preferences done in an industrial design community in 2019. This Rhino 3D modeling software that we use was the most popular software among users during that year. Next, we will demonstrate how to download and install this software, as well as a basic operation of its interface and ways to control the model. Through 3 stages of practical exercises, students can familiarize with the execution of commands and modeling techniques. So now students can start to draw your own 3D model of your compressed air racing car. Here is a demonstration of how to download the Rhino 3D drawing software used for the learning of 3D modeling. Open the browser. Type in Rhino 3D, RHINO 3D, and you can find Rhino's official website. Here we select the Download tab. Depending on the operating system that you use, you can download the trial version software for Windows or Mac. Here the teacher will download the trial version of Rhino 6.0. you just need to enter your email account. To download and install the Rhino 3D drawing and modeling software. After downloading the software, we click on the download folder, then click on the Rhino 3D drawing software we downloaded. And we can start installing the software. After installing Rhino, we click on the Rhino icon on the desktop to open the Rhino 3D drawing software. It is recommended that when choosing the file format, we choose small objects, millimeters, so that the size ratio for the drawing of our model corresponds to the design of our compressed air racing car. After opening the Rhino template, we will see that there are 4 panels on the screen, which represent the front view, top view, right view, and perspective view. I will draw a cube to explain what each of these views represent. There is a cube command here in Rhino. You can left-click your mouse to select this command. I will draw a long rectangle at the top view, while at the front view, I will drag it to a certain height. And you can see this model in the perspective view. Here I right-click and hold the mouse to rotate the model so that we can view this model from multiple angles. The current model only shows the frame lines, so this is called the wireframe display. If you want to see more clearly, you can right-click your mouse in the perspective view and select the shaded display. Likewise, in the front view, we can also right-click to change to shaded display. The top view can also be changed to shaded display, and the right view can also be changed to shaded display. Here I will explain the angles of the front view, the top view, and the right view and their relationship. In terms of this 3-dimensional square, if we turn in this direction, it represents the shape of the front view. So you can see these 2 shapes are the same. The top view is to look at this model from above. I will rotate to an angle from top to bottom. And you can see that this shape is the same as the top view. So in the same way, let me go back to the front. When we see this model from the right side, it represents the right view. So this is consistent with the concept learned in graphics. Front view, top view, right view. This is the 3rd angle projection method, which is what we call the orthographic projection planar drawing method. Its relative position is that top view must be above the front view, and the right view has to be placed to the right of the front view. So this is the basic concept of graphics. The upper right corner shows the 3-dimensional shape, which helps users view its 3-dimensional relationship at all times. Next, we will demonstrate how to switch between panels in Rhino and control the model. In the Rhino environment, we click on each panel, and it will automatically switch to the operation of such panel. For example, I click on the front view panel, it will switch to the operation of the front view. I go back to the right view and click it, and it will automatically switch back to the right view. In the top view, let's say I feel like I need to enlarge it to work on it. I can left-click twice in this place on the top view and enlarge it to a full screen size so as to facilitate my drawing. In the same case, I left-click twice here on the top view and it will switch back to the original 4 panels. This is the way of switching panels in Rhino. I will repeat it again. For example, if you click twice on the front view will be maximized. Click twice again, and it will switch back. Left-click twice on the right view, and it will be maximized. And left-click twice again to switch back. This is for switching between panels. Regarding the control of the model, we can change the size of the model by turning the wheel in the planar view. Right-click and hold to move the position of the model. This is the way to control the model in Rhino. For example, I click twice on the top view to maximize it, and if I want to enlarge the size even more, I turn the wheel to zoom in to do the control needed for our drawing. This is the way of adjusting the model that we often use in Rhino. Right-click and hold in the perspective view to rotate the model. Since it is not possible to rotate the viewing angle in any planar view, so right-clicking is defined to move the model. Rhino's command interface can be divided into graphic type commands on the left side. At the top of the graphics commands, here is the selection tool and the point tool. These 8 icons are all styling commands for drawing lines. These 2 are commands for drawing or editing of surfaces. These 2 are commands for drawing and editing of solids. These last few ones, some of them are for grouping, exploding, copying, and trimming, and these are other application commands related to the operation of 3D models. The upper part can be divided into 2 parts. This part is a menu type command. When you select the menu, the relevant commands will be listed for you to use. The same goes for the display and select menus. These at the top are text type drop-down menus. In our menus, text descriptions are used to explain the operation commands. This is the way commands are arranged in Rhino. Here, we will use a solid command to explain model control in Rhino. If we click our solid tools icon for a bit longer, we can change the shape command. There is cube, sphere, ovoid, parabola, cone, truncated cone, and pyramid. These shapes can be directly drawn as a 3-dimensional shape. For example, I draw a square on the top view panel from the coordinates origin to a distance of diagonally 3 times 3 large grid segments, and then a height of also 3 segments. This kind of drawing, we may think that the size is 3 times 3 times 3, but when we enlarge the model to a certain extent, we realize that we did not actually align it to the position that we wanted. So it's not very accurate for us to draw a model by visual observation. Here I draw another 3 times 3 centimeter square. Through object snapping for you to see. This time, we enable grid snap and object snap. We again use the cube command. You can see that now the cursor is like a magnet and will attach to these points. Again, I will draw up to 3 grid segments diagonally, and then in the front view, I will drag its height up to 3 segments. Okay, at first glance, the 2 models look like the same size, but we have just proved that at this point, it is not precisely at 3 centimeters. I'll zoom in this model on the right for everyone to see. It is, in fact, precisely locked into the position we want. It is so for its left side and also for its right side. Therefore, when modeling in Rhino, we often need to enable the grid snap and the object snap modes in order to draw our models more accurately. For the following procedures, I will demonstrate using similar methods. We don't want this model on the left anymore. Next, I'm going to draw a cone next to the cube in the same way by using the cone command inside the solids tool. For this cone, I would like its base area to be 4 centimeters diameter, so I'll look for 2 large segments. Then it can be pointed upwards or downwards. You can also draw up to 3 centimeters in the front view panel. This is the cone that I drew. Next, I will draw a sphere. This sphere command is also found inside the Solids tools. In the same way, I will draw a sphere with a 4 centimeter diameter. Next, I will do some moving, copying, and transformation operations for you all to see. There are many ways to do this part. There is a great tool in Rhino 5.0, which is called Gumball in English. For Gumball, we select an object, a point is defined at its center, and there will be some cursors. We click on the cursors, and in the green axis direction, red axis direction, or blue axis direction for height. We can control it with precision. This way, we can move the object to the position we want. For example, if I want to make an effect similar to the stacking of building blocks, I will move the sphere on top of the cube. I will align it right in the top view panel. And then in the right view panel, I will adjust the height to the position I want. Then, I will put the cone on top of the sphere. In the same manner, by controlling the gumball, I will move up in the green direction and adjust accordingly in the red direction. Then in the top view panel for the front and back depth position, put it in the same position as the sphere. Then open the perspective view panel, so through the movement of the gumball, we can accurately place each 3D model in the position we want. This is the operation method of the gumball. You can carefully see that there is a square at the endpoints of each arrow of the gumball. For example, there is a red square at the endpoint of the red arrow, a green square at the endpoint of the green arrow, and a blue square at the endpoint of the blue arrow. This square is for the scaling of the axis. For example, now I'll click on the blue axle square. Then I can go inwards to turn it into a flattened cone, or go outwards to turn it into a fat cone. The scaling only works in that axle direction. It will only scale in the blue axle direction. The red axle direction will remain 4 centimeters. As you can see from the top view, the red axis is still 4 segments, but the blue axis has been elongated to more than 5 segments, so it becomes an oval. This is Rhino's gumball being able to scale in a single axis. So in the same way, for example, I want this cube to be fatter in the green direction. I will pull the green square, and it can elongate. For the sphere, I also want it to be fatter in the red direction. So I click and hold the red square, and it gets fatter. So our model turned into this, with its scaling in a single axis. In addition to scaling, using the gumball tool, we can also go some angular rotation controls. For example, the blue arc, the red arc, the green arc. It will rotate with respect to the blue axis, rotate with respect to the red axis, and rotate with respect to the green axis. For such operation in this 3-dimensional environment, it may be difficult for us to control the rotation according to a specific angle. This situation makes it difficult to control the rotation angle between the models. Therefore, for the rotation of the gumball, it is generally recommended to be operated in a planar view. So I will use the Ctrl-Z on the keyboard to restore the model to its original angle. I will perform relative operation in the top view panel. For example, for this rectangle, I will rotate 45 degrees with respect to the blue axis. I click on this the blue axle arc and directly input 45 degrees, and then it will rotate 45 degrees. This kind of control will be more accurate than by moving through dragging. This is the use of the gumball. I will repeat the operation again. For example, I select the oval sphere in the front view. I want it to rotate 45 degrees with respect to the green axis. The same way, I input 45 and press enter, and it will be the angle of rotation. The angle you see with the cursor here is 45 degrees. This is the use of the gumball, which can be controlled through input. So, I'll demonstrate again. In this right view panel, input with respect to the red axis for it to rotate 45 degrees, and it will rotate 45 degrees. The final angle of this model will be like this. We can also use the gumball to perform a copying action. For example, I select this cube. After I select it, I press the Ctrl+C keys and then press the Ctrl+V keys to copy an identical model. Then I use the rotation function of the gumball to adjust it to a 90 degrees rotation. And now, there are two shapes forming a cross. In the same way, I do the same with the oval sphere. After I select it, I press Ctrl+C, then Ctrl+V, and then with respect to the green axis, I also rotate it 90 degrees. In the same way, it will show a cross with these oval spheres. Finally, in here, after I select it, I press Ctrl+C, then Ctrl+V. With respect to the red axis, I rotate it 90 degrees. This way, we will produce this situation, where there are pairs of shapes crossing each other. So far is the demonstration of how to use the gumball in Rhino 5.0 to control these models, adjust their angles, and copy them. This part's demonstration is now over. We have learned about the basic operations of the user interface in Rhino. Our next topic will be using commands to perform the first stage of modeling learning for our compressed air racing car. Here we open right view panel. Click to enlarge. We will first draw in this panel the tires needed for our compressed air racing car. First, we select the polyline command. When operating in Rhino, we use the left button of the mouse to select commands to find the relevant coordinates or select the relevant objects. This point of origin on the screen, which is origin of the global coordinates. At the intersection of red and green lines, we draw upwards 4 millimeters. Then a depth of 1 centimeter, then upwards 1 centimeter, with a total height of 1.5 centimeters. Then go inwards back to our green axis, then go up 3 squares, and then we keep a distance of 3 squares from the lines before it. Here we have completed the first contour lines that we need. You can see that these are line segments drawn one by one from this polyline. Because we have both grid snapping and object snapping enabled, our position is accurately aligned with the grid points. So what we drew will be of whole number values. Next, we will switch to the 4-panel screen. In the perspective view, we can see that what we just drew was a planar contour line. Here we will rotate this contour line with respect to the green axis, and it will become a 3-dimensional solid model, which is the tire shape we want to get. Inside the surface modeling tools, with the left button of the mouse, we select the fifth from the bottom command. Select our object. To tell the computer we're done with the selection, we have to press Enter. In here, the right mouse button has the same meaning as the Enter key on the keyboard, which means Enter, so I just press the right mouse button. Then we tell the computer where we define the location point, which is the front view where the cursor is right now. So we find this point at the origin of the coordinates and tell the computer that we are finished defining the point. We press Enter again, or also clicking the right mouse button. Here, we will see a 360-degree circle and an axis. This is for us to input 360 degrees directly, or, as seen on the screen, we can define the tire to rotate to 270 degrees, which is the meaning of rotational molding. However, our tire basically needs to rotate 360 degrees completely for it to be a complete 3D model. So let's review the command. Inside the Surface Modeling Tools, select the Revolve command fifth from the bottom. Select our object by clicking with the left mouse button. Once selected, we click the right mouse button. Next, we define the center of rotation, which is the origin of the coordinates. And then press Enter again to tell the computer that we've selected the origin of the coordinates. Then select directly 360 degrees on the command bar, and it will directly complete a 360-degree revolved model. We can open the perspective view and see that this model is the tire that we want for our compressed air racing car. After these two operations, you will realize that for the commands in Rhino, we use the left mouse button to select the commands or select the defined position. To tell the computer, the step is to press the right mouse button. Again, let's do another demonstration. We need rivets for this solid. That is, the edges of the tire need a rounded shape. Here we will use the body editing tool. Next to the cube, there is an icon of two spheres stuck together. Press and hold to pop out the window and choose the fillet command. After selecting the command, we tell the computer the places processed are these two edges of the tire. Here is to input the fillet radius. Our current default value is 1. Let's see how it looks with value 1. We press Enter directly and see that we turned the originally sharp edges of the tire into an arc shape. Next, at the corner of the inner side of the tire, we want it to have a larger fillet. To prevent that our 3D printed tire from having stress concentration issues at these places where strength is needed, which can cause damage to the tire. So in the same way, we also use the fillet command inside the solid editing tool. Select next radius and input the value 3 so that the fillet can be larger than the previous one. Then select our edges. Select these two places and tell the computer we are done with the selection by clicking the right mouse button. This time, we can get a larger fillet at the corners of the tire and the inner face of the tire. Now, by drilling an axis hole, we can finish with the tire's basic structure. Here, we can directly use the solid modeling tool to create a circular rod by using the cylinder command. In the front view panel, select this point at the origin. We enter a diameter value of 3.5 millimeters. And in the top view panel, we drag a cylinder that is longer than our tire. I'll select it for you to see. At this moment, it is going through the front and back of our tire. Next, we will use this cylinder to drill out an axle hole shape in our tire that can be used as a 3D printed tire. What we need to do next is the processing of the model, that is, using the Boolean operation inside the solids tool. There are 4 types of Boolean operations. One is union, another one is difference, so here we should be using Boolean difference by doing subtraction. The command bar will remind us what to do next. Here it tells us to select the surface or multiple surfaces to be subtracted, which is the tire, and we need to press enter. Then select the surface or multiple surfaces used to trim the other object, which is our cylinder. We tell the computer we are done selecting, and likewise we press enter, and we have completed a tire with an axle hole. Next, in the front view panel, we use the gumball to copy the tire and move it to the back, and move the original tire forward. Here we need to check our compressed air racing car's side contour line. We make an overall design plan based on the position of the tires. For example, we align the axis of the front wheel to a distance of 3 centimeters from the edge. The rear wheels is also at a distance of 3 centimeters. Then we draw the side contour of our compressed air racing car. We use the control point curve command. To draw the contour line for the side, of our compressed air racing car. And then we connect the two ends with the polyline. This contour line here will be used as the waistline of our car body. We want the tires to move up a little so that it can be hidden under the waistline as the hub of the front wheel. The same goes for the rear wheel. We move it up 5 millimeters, and this will be the hub of the rear wheel. Once we are finished, the skirt line and the waistline, we combine them together into a closed loop curve. Here, we will do a 3-dimensional extrusion. The command is inside the Solids tool, the third one from last, Extrude Close Planar Curve. Select the command, and then select the contour line we want to extrude. And press Enter. Here we can choose both sides or a single side to extrude our contour. Okay, we extrude 2 centimeters, then we move this extruded solid until it covers the tires. Next, let's complete a car roof, which is a contour between the shoulder line and the roof. We also use the control point curve command. In the same way, we start from this end point and draw a surface with low inclination as the roof. We need to go up because the design parameters require 5 centimeters height. From the bottom of the car, we go up 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters, and 5 centimeters. The car body's highest point should reach up to here. We extend backwards. Here we want to mount the steel cylinder 4 centimeters above the skirt line. So here we go up a little bit so that our cylinder can be closed at this height. Here we can reduce some weight so we surpass our axle to the front of the wheel and make an ending. This is the contour line of the center of our car body. In the same way, we draw a straight line to close the endpoints. This contour and the line we just drew at the bottom of the car, we will combine them together, and then we switch to the perspective view panel. Again, let's repeat the extrude command. In the same way, we select the extrude closed planar curve command inside the solids tool. We will cancel the options to extrude on both sides. Here, we observe the width we need. Previously, we extruded 2 centimeters over here, so we will add 4 centimeters for the middle part. For this last segment, we will use the gumball to copy and move it over here to add 2 centimeters more. Therefore, 2 plus 4 plus 2, we have fulfilled the 8 centimeters width requirements for our compressed air racing car. For these 3 solids that we've completed, we'll do a Boolean Union. We select the first one, Boolean Union, select the first model, the second model, and the third model. After all the models are selected, press Enter and it will become a complete model. Next, we will carve out wheel arches in the car body for our front and rear wheels, so that our wheels can spin within the body, as well as the space where we can place our steel cylinders at the back of the car. We switch to the front view panel and maximize it, and we use this cylinder command with respect to the center of the wheel. So we enable grid snap and center point. We approach it and draw a cylinder slightly larger than our tire. We check the top view. We want to cut out 4 millimeters more than the width of the tire. This is the cylinder that we want to use to create the wheel arch for the front wheel using Boolean difference. The same goes for the rear wheel. We use the gumball to copy and move this cylinder to the rear wheel. We copy another cylinder to the center of the rear wheel. Let's switch to the top view. These are the 2 cylinders that will be used to make the wheel arches of the left side. We use the mirror command so that the right side has the same cylinders. The mirror command is inside the Modify tool with an icon that looks like a saw. Based on the center of our model, we make an axis of symmetry. By pressing and holding the Shift key, it can align to the horizontal direction, so that the right side of the car also has the same cylinders. We will use Boolean difference to subtract the space we need for our tires. So we first select the tires. Click the light bulb to hide them. Let's have a look from the bottom. For Boolean difference, we select the second icon and select the car body first, which is the multi-surface that we want to keep. Press Enter and then select these 4 cylinders to carve out the wheel arches that we need. Next is the space at the back of the car, where we will place the steel cylinder. We open the right view panel. Here we will draw a cylinder at the position we need. We draw a circle with a diameter of 18 millimeters, so at the command bar, we input 18, the diameter of the steel cylinder. Because our steel cylinder is a small one of 6 cc, so we move it to the right up to a depth of 5 centimeters from the end of the car, and then we stop. Here we will adjust it to the height we need. We adjust it to the height we need at 4 centimeters height. And then we do a Boolean difference again. We select Boolean difference, first select our car body, press Enter, then select this cylinder. We have completed the space needed for placing our steel cylinder. Finally, in order to match our chassis design, our tires are pierced through from left to right, and we need holes to pass through the axles. So we repeat the Boolean difference to carve out the axles. We will draw two cylinders in the front view panel. Based on the center of our wheels, we draw a cylinder with a diameter of 1 centimeter and a length that can pierce through the whole body, and move it to where it pierces through the left and right side. We'll also draw a rectangle. We will use the quadrant mode to get the left and right side of the cylinder as well as the very back end. You can see the combined shape of the cylinder and rectangle. We will use Boolean Union to merge them. Then we copy this same model to the position of the rear axle. Let's go back to the perspective view. Finally, we need to use these two solids to make a design for the axles to pass through our car body. We use Boolean difference. First select our car body, press enter, then select these two solids and press enter. And here we have completed the appearance of our compressed air racing car. Let me turn the model around for the students to see. We put the tires back. We right-click the light bulb to display. We do the same with these tires. We mirror them to the other side of the car. The mirror command is inside here. Along the central axis of the car, we mirror them to the right side of the car. Then we remove these lines. And here we have completed the design of a compressed air racing car. We can choose the display mode to a rendered display to see the appearance of our entire model, or the ghosted display to see if the spatial structure design inside our model is reasonable or not. And we have completed Rhino's basic command learning and the basic modeling design of a compressed air racing car.